Hi, George Diamond here. Now today we're going to take a look at something called the trapezoidal rule. I've been doing a little bit of painting, so I've got my can of yellow paint still. Let me put this down. So we're going to look at something called the trapezoidal rule. Now in our textbook this is section 4.6. Now the trapezoidal rule is another technique for estimating the area between a curve and the x-axis. Now in my last video we looked at using Riemann sums. So left-hand Riemann sum, LREM, RREM, and MREM. So if you want to see the technique for using rectangles to estimate the area between a curve and the x-axis, you can see my last video. But now with this technique here uses trapezoids, the area of a trapezoid, to estimate the area between a curve and the x-axis. Now you got to remember now to do this. The trapezoidal rule is based on the area formula for a trapezoid. Now, if you remember the area of a trapezoid, you're given a trapezoid. This down here is going to be your two parallel bases. So base 1, B1, and B2 are two parallel bases. And then you got the height. The height is always the distance between the two parallel bases. And if you remember now, the area formula for a trapezoid is 1/2 times height times the sum of your two bases. So base 1 plus base 2. And now the reason we look at estimating the area, or estimating the area between a curve and the x-axis, we're estimating a definite interval, is because there are some integrals that are, I won't say impossible, but they're very, very difficult to find the antiderivative of. Now we're going to look at some real simple examples here today, but the same technique can be used to estimate the area between the curve and the x-axis of virtually any definite interval. So for instance, I got a little example here. If we needed to estimate the area between the curve and the x-axis from 2 to 4 of sine x squared, now that would be very difficult to do. Alright, so the antiderivative of sine x squared is simply not an elementary function. So I mean, you have to use complex numbers or something, but it'll be very, very difficult to find the area between the curve and the x-axis of sine x squared. But if all we're looking for is an estimate of the area between the curve and the x-axis, then we can use trapezoids, we can use rectangles to estimate that. Typically the trapezoidal rule usually is maybe sometimes or usually a little bit more accurate than using Riemann sums with the rectangles. But like I said, this here would be very, very difficult to estimate this using the fundamental theorem of calculus. Finding the antiderivative, substituting the upper bound minus the lower bound, this would be very, very difficult to do. But we can estimate the area between the curve and the x-axis using the system of trapezoids. Now we're going to start off. Let's see if we can come up with a derivation of the formula or the expression that we're going to use to calculate or to estimate our area using the trapezoidal rule. So let's take a look at how we come up with our formula here. Now I'm going to use my example here. So as you look at my curve here, this is my curve f of x. You can see I've got 1, 2, 3, 4 trapezoids here. Now to get the height of our trapezoid, now the height would be this bottom base down here. So from x0 to x1 would be the height of the first trapezoid. Now to get your height, you have to take the upper bound minus the lower bound. So b minus a divided by n, where n is going to be the number of trapezoids. Now keep in mind, most of the two examples we're going to use involves 4 trapezoids. 4 trapezoids will give us an estimate of the area between the curve and the x-axis. 4 trapezoids is good. 8 trapezoids would be even better. Would give you a more accurate estimation. 80 trapezoids would be even better. But then the calculations get crazy. Trying to add all those areas of each of those trapezoids together. So the more trapezoids you use, the more accurate your estimation will be. So we're just going to use maybe 4 trapezoids or so for our estimates here. But let's take a look at where we come up with our formula. And so as you look at, erase this down. Okay. Now as you look at our trapezoid here, to estimate our area here between the curve and the x-axis, okay, we're going to use our area formula for a trapezoid. This is the area of a trapezoid. Now, if you look at this first trapezoid here, all right, so if we look at that first trapezoid, the area of a trapezoid would be 1/2 times the height. And we said the height is going to be b minus a divided by n. All right, so 1/2 times the height times the sum of your two bases. So if you look at this first trapezoid, the one that's outlined in red, the first base would be where this edge of your trapezoid touches the curve. So So the first base here would be the function at x of 0, okay, plus. Now the second trapezoid will be where the other base touches your curve. So this would be the function at x of 1. So this will describe the area of the first trapezoid. Now the second trapezoid would be 1/2 times the base, which would be b minus a divided by n. Now the second trapezoid, now notice now that the second trapezoid and the first trapezoid share a side. So the height of this trapezoid we said is a function at x of 1. So this will be the function at x of 1. Okay, plus, okay, the base of the next trapezoid. So the height of this base or the length of that base would be the function at x of 2. Okay, plus 1/2 times the height again, which would be b minus a. Let me see if I can bring this down here so it's a little bit easier to see. All right, so plus 1/2 times b minus a, okay, divided by n, okay, times, now let's see our third trapezoid, this is our third trapezoid, will be the function at x of 2, okay, plus the function at x of 3. Okay, f of x of 3 would be the height of the next base or the length of the next base. Okay, plus 1/2 times b minus a divided by n, and then the last trapezoid down here, you got the function at x of 3, okay, plus the function at x of 4. Okay. Now you notice here's our 4 trapezoids. Now each trapezoid has 1/2 times the base b minus a divided by n, so your height. So our area then we're going to describe as would be approximately equal to, so they're not exactly equal to, but we'll describe our area as 1/2 times b minus a, okay, divided by n. So what I'm going to do is, as I finish up my description here, I want to factor b minus a off each of those. So each one of them has b minus 1/2 times b minus a as a factor on each, so we're going to factor that off. This becomes 1/2 times b minus a, okay, divided by n. Okay, times, now if you look at your trapezoids here, okay, we've got we'll have a couple of like terms. First of all, we have this is going to be one base here, so the f of x of 0. Okay, plus now you know you got f of x of 1, f of x of 1 again. So where the first trapezoid and the second trapezoid share a common side, we're going to have 2 f of x of 1. So it'll be 2 times f of x of 1 plus, and then 2, we've got 2, get f of x of 2, and we got f of x of 2 again. So it'll be 2 times f of x of 2, okay, plus 2 times f of x of 3, okay, plus, now you notice now down here at the end, we only have 1 f of x of 4. This is going to be this last base down here. Well, the last base is only used by that last trapezoid, so we only have 1 of them, so this will be f of x of 4. So this is going to describe our area here. Now notice a couple of keys here. The first base is only used once, it's 1, 2, 2, 2, and then 1 again. So as you look at the actual expression, I guess, if you look at our textbook, if you look up the trapezoidal rule in our textbook, this is what it will say. So the area is going to be approximately equal to b minus a divided by 2n. So they're going to multiply the 1/2 and the b minus a over n. So it'll be 1/2 times this, it'll be b minus a over 2n. F of x of 0 plus f of x of 1 plus f of x of 2 all the way down to f of x of n, 2 times rather f of x of n. This will be 2 also. Let me write this again. So you have 2 of them, so it'll be 2 times f of x of 1 plus 2 times f of x of 2 plus all the way down 2 times f of x of n, okay, plus f of x of n minus 1. That's 1 times f of x of n minus 1. So if you look at our textbook, this is the expression they use. And like I said, it basically comes down from the area formula for a trapezoid. So you have 1/2 times the height times base 1 plus base 2 and then all the other bases. So it's basically, so really, as far as memorizing your formula here out of our textbook, you just have to really remember the area formula for a trapezoid. 1/2 times its height times each of your two bases. Now you want to notice now, on our bases down here, the first trapezoid, or the first base is only used one time, and the second base is only used one time. So if you look at these numbers here, you can have 1 plus 2 plus 2 plus, right on down, 2 plus 2 plus 1. So if you look at your bases, okay, these are the coefficients on your bases. All right, so the first base, all right, so the first base here is only used one time by the first trapezoid, and the last base down on the end is only used one time by the first trapezoid. All the bases in between are going to be used 2 times because they're going to be shared base for 2 different trapezoids. So the bases, so if you look at the coefficients on each one, they go like this. So 1, then all the rest of them are 2, and then the last one is 1 also, so 1 coefficient. So let's try a couple examples. We're going to do 3 examples. We're going to do just a little polynomial example. We'll do a trig function, and also we're going to see if we can do a data problem, right? Because those students that are taking the AP Calculus exam, you see these all the time where they're given a data problem, and you have to estimate a particular area using trapezoids. So we'll try a couple of these. So using the trapezoidal rule. So we'll try several examples. And once you've got the process down, this is actually pretty easy to do. So let me erase this. Okay. Like I said, some definite integrals are very difficult or almost impossible to estimate. So I'm going to go ahead and bring these here. Here's our first problem. I'm going to set it up here. So I've already, just to save a little bit of time, I've already got the graph done and everything. So we're going to estimate the area between the curve and the x-axis from 0 to 2 of x squared. Now, keep in mind, if you're familiar with the fundamental theorem of calculus, it would be a very simple matter to find the antiderivative of x squared. Substitute the upper bound minus the lower bound, and we could get the exact value of the area between the curve and the x-axis here. But let's see if we can do this one. Let's see if we can estimate the area using the trapezoidal rule. So we'll see if we do a little estimate here. So as we get started, now first thing I like to do is describe our height. So we got to get our height first. Now the height. In this case, we're estimating the area between the curve and the x-axis from 0 to 2. So we write our integral over here, so 0 to 2. So x squared dx. All right, so from 0 to 2. So to get the height would be 2 minus 0. And we're going to do n equals 4. Now n equals 4 is the number of trapezoids. So we're going to have 4 trapezoids. So to get our height would be 2 minus 0 divided by 4, which gives us 1/2. Or 0.5. So every 1/2, we're going to start a new trapezoid. So from 0 to 2, we're talking about this region right here. All right, so let's see, that would be 2 trapezoids. We need a 0.5 in here, and a 1.5 here. So if you look at our trapezoids, this is what it's going to look like now. All right, so we're going to see if we can find the area of each trapezoid, and then see if we can estimate this. Okay, also another thing I want to point out is you look at this curve, and if you look at the top of the trapezoids here, okay, this curve is concave up, it opens up. Right, so whenever we estimate this, you can see a little bit of the trapezoid here at the top is going to be above your curve. Right, so when we estimate this, I would imagine that the estimation is going to be an overestimate. So where this is concave up, you can imagine a little bit of the trapezoid here is going to be above your curve. So this should overestimate what would be the actual area between the curve and the x-axis. Now, if you have a graphing calculator, pretty quickly, you can put this in your calculator very quickly. It'll give you the area. Or it'd be a simple matter to find the antiderivative, substitute the upper bound minus the lower bound. So we can get the exact area very quickly. So as we set this up, so we're going to do, as we estimate our area, so our area is going to be an estimate. Right? So this would be 1/2 times the height. Now the height we said is going to be 1/2, so 1/2 times. So times, let's see, now we're going to do the function So we'll do the function at 0, so from 0 to 2, right? So every one half we're going to have a new trapezoid. So this will be the 1 times the function at 0 plus 2 times the function at 0.5 plus 2 times the function at 1. Erase this here too. So we got our height. So at 1, okay, plus 2 times the function at 1.5 plus. Now see the last at 2, you're only going to use the last base here 1 time. So plus 1 times the function at 2. All right, so as we describe this now, this would be 1/4. So 1/2 times 1/2. So 1/2 times the height of your trapezoid. And these are your 2 bases here. So as you look at the area formula here, so this is simply 1/2 times the height times, and this will be base 1 plus the rest of your bases here. Okay? So as we set this up, this will be 1/4 times the function at 0. So now the original function is x squared, so we'll substitute 0 in for x squared. This will be 0 squared plus, then 0.5 in for, so it'll be 2 times, so we can get the 2 in here, so it'll be 2 times the function at 0.5. So 2 times 0.5 squared plus 2 times 1 squared plus 2 times 1.5 squared plus 1 times, and then this last one down here will be 1 times 2 squared. Now, if you've got a calculator, very quickly you can punch this up on your calculator. Now, when I did it, I got 1/4 times 11. You get 1/4 times 11, which is about 2.75. So 2.75. Now, keep in mind the actual. I also did this earlier using the fundamental theorem of calculus. So the actual area was 2.667. So you can see 2.75 is a little bit over what the actual area would be. So 2.667 is the actual area. For our estimate now, we got 2.75. So you can see actually, pretty close. So fairly close. Okay, let's try example number 2. Now this time we're going to try a trig function. So let's try some trig function. And let me erase this. All right, so here we go. So let's try a trig function. Now for our next example this time, let's try the estimate. Problem number 2. Okay, let's see if we can estimate the area between the curve and the x-axis from 0 to pi of sine x. Right. Now, very quickly, we could, this would be a simple problem to find the exact area between the curve and the x-axis. We have to find the antiderivative of sine x, substitute the upper bound minus the lower bound, and very quickly we could get the area between the curve and the x-axis here. So this would be a simple one to do. It actually would be easier to use the fundamental theorem of calculus and find the antiderivative than it would be to actually do the estimate here. But we're going to, just to illustrate how it's done, so we'll do our estimate. Now, as you look at your curve here, now once again, we're going to do n equals 4. I thought about doing 8 subintervals, but trying to get all this on my marker board up here would be, it's just hard. So the same process works with 8 as it works with 4. All right, so to start off, we need to get our height. So let's describe our height. And the height here, we're going from 0 to 4, and let me write our integral over here too. So it'll be integral from 0 to pi sine x dx. Now, I may need to take this graph down in just a moment, so if you need to write it down, you need to go ahead and copy it into your notes right now. If we get our height, this will be pi minus 0 divided by 4. So with n equals 4, that means we're going to use 4 trapezoids again. So n equals 4. All right, so the height here is going to be pi over 4. So pi over 4. So if you look at your trapezoids, this will be 1. So if you look at your trapezoids, this is it. So like this right here. Now, you'll notice that with this particular trapezoid, let's see, it should be pretty close. So we'll see how close we get to what would be the accepted area here. So the accepted area. So as we set this up, now we're going to use I'm going to set this up as using my area formula. So our area is going to be 1/2 times the height. Now the height will be pi over 4 times. Now let's set up our bases. Now the first base here is going to be 0. So this will be, as we set this up, this will be sine 0, so 1 times sine 0 plus, and then the next base will be pi over 4, so it'll be 2 times sine pi over 4. And we erase this here. Okay, plus 2 times sine 3 pi over 4. Okay, plus, now the last base here we just use 1 times, so this will be 1 times sine of pi. Okay. Now this will set it up. Now notice how your coefficients go as you substitute each of these into your original function here. So you got 1, 2, 2, and then 1 again. So the ones on the end, those bases are only used 1 time, or all the ones in the middle are used twice, right, by 2 different trapezoids. All right, so let's see, make sure I get that. So it'll be 0, 0, pi over 4. Actually, I left 1 out here. Let me erase this again here. I'll just count. Let's see the number that we have here. This would be, so it should be sine 0, then pi over 4, and then plus, you're going to get this right, so it'll be 2 times sine of pi over 2. So I left that out. So plus, and this would be 2 sine 3 pi over 4. Okay, plus, and then 1 times sine pi. 1 times sine pi. Okay, this is it now. Right. Now, as we, and I've already calculated this, the estimated area here is 2.126. So 2.6. That's a pretty good, actually pretty close to what would be the accepted area between the curve and the x-axis. All right, so we've done a couple examples. So once again, this will be 1/2 times your height, which is pi over 4 times, and these are your bases. And this will give you a good estimate. So with a function like this, it's actually, it's not too difficult of a calculation. That nowadays we have these graphing calculators, which makes it much easier to do. So now let's try a problem that's a data problem. So we have students that are going to be taking the AP Calculus exam. If you're taking AP Calculus in high school or something, you see these types of data problems all the time where they ask you to estimate area from a set of data. So let's try one of those problems too. So take this off. Bring this up here. Okay. Now this will be our third example and our last example. So we'll finish up with this problem here. All right. Now, so we're going to estimate the area between the curve and the x-axis from 1 to 7. Okay, using a trapezoidal sum with 3 subintervals indicated by the data. So 3 subintervals indicated by the data here. So, so let's see. So indicated by the data. All right. So let's see. We're going to do 3 with 3 subintervals. That means we're going to be using 3 trapezoids. All right. So 3 trapezoids. And now, I'll tell you what, let's do. Let's do this one thing that may help whenever you're doing a data problem like this. You can just do a quick sketch of your data, make it a little bit easier to kind of visualize what it is you're doing here. So this would be, so we'll do just a real quick sketch. You can see my biggest number is 40, and goes from 10 to 40. So go 40 here, 20, 10, and 30, and then we go from 1 to 7 on the x-axis. So put 8 here, 4, 2, 6. 3, 4, 5, 6, 7. All right, so let me just do a little sketch here. Now, first point is at 110, so 110. Next would be 420. About right here. 110, and then that's 640. So 640 would be about right up in here, and I'm just estimating this. And then 730. So 730 would be right about in here. Now, so if you look at these trapezoids, that'll be our first trapezoid there. And the next trapezoid, that's going to be trapezoid number 2. And then the third trapezoid will be this one right here. Now, you notice now with these data problems like this, the height is different with each trapezoid. So you're going to, the problem says to use a trapezoidal sum with 3 subintervals indicated by the data. So a lot of times on these data problems, the base on each trapezoid is going to be different. So we're not really going to be using that formula that we looked at a minute ago, where you're working with a base of even intervals, right, for the height on each trapezoid. So this is a little bit different. So basically, we're going to describe the area of each trapezoid and then add them all together. Right? So we're only going to do 3 here, so it shouldn't be too difficult. So we describe our first trapezoid. Right? So our area here is going to be, so approximately, now the first trapezoid would be 1/2 times the base. Now the base would go from 1 to 4 here, so this base here would be, so the first base is 3, the next base is 2, and then the next base here would be 1. All right, so the first base here is going to be 1/2 times 3, and the height of the first base here would have a height of 10, so it would be 10 plus. Now the next base has a height of 20. All right, so 10 plus 20, okay, plus. Now the next trapezoid, the next trapezoid would have a height of 2, so it would be 1/2 times 2 times. Now the first base here would be 20, and the next base would be 40, so it would be 20 plus 40, okay, plus, and then the last trapezoid down here will have a height of 1, and the two bases, the one base will be 40, the other base will be 30, so it'll be 40 plus 30. Now, also you'll notice now that the 10, the first base is only used one time, the 30 is only used one time, but the 20, you see 2 20s and 2 40s in there, right? So they're going to be, you have two shared bases there, so you got both of those. Now, as you calculate, if you do your calculation here, let's see, this would be 30, 15, 3 would be 45 plus, and let's see, plus, our height, what was our height? This is 2, so 1/2 times 2. So 1/2 times would be 3, this would be 2, 1/2 times 2, and then 1. So this would be 60, so 45, 60. Okay, plus this would be 70, half of 70 is 35. Adding those up gives us 140. All right, so this would be an estimate of the area between the curve and the x-axis of 1 to 7 of this set of data. So, so one thing, if you're taking the AP Calculus exam, they can't really give you you only have a certain amount of time to do each problem. So, they're not going to ask you to do, more than 8 trapezoids, usually less than that, maybe 4 or 5 at the most, 3. Like this problem here. So they're not going to ask you to do a whole bunch of trapezoids because it just takes too long to do. But like I said, you got to be careful with the data problem because typically the height of each trapezoid down here, the height of each trapezoid is going to be different. So you just kind of have to watch that. Now my students, when we do their homework, I'm going to give you several of these data problems to look at, because if you're going to take the AP Calculus exam, you'll more than likely you'll have to do some type of estimate like this, either using rectangles or trapezoids if you take the AP Calculus exam. You do see these types of problems all the time. Now, that's my last example, so hopefully you have found this video helpful. And now let's go to your homework now.